this is what? This is lecture. What, 40, I think? So let's look at, I'll give you some hints for this. Homework number 11, hints.
And then there's also one more lecture on Canvas. So is that also for Friday? There's a lecture on Canvas.
Yeah, there's actually, all of them are on there. If you go to Canvas's front page, so that's actually, I should have pointed that out. I didn't really mention that yet. Yeah, so check this out. If you go to, if you go to our Canvas page, so if you go to Canvas and you click on our course, the first thing that's going to pop up are the YouTube lectures are embedded. This is a link. This is all the lectures. It's not just one of them. It's all of them. So if you watch this, you'll see we did problems 1 and 4 on Friday. So I would encourage you to check that out. And if you still have questions about it, please let me know. But all the lectures are here now. If you click on it, it should take you right to them. There's a typo, so it should be 1,000 at the end. Does that make sense?
Yeah.
Yeah. So I pointed out there are, I didn't fix them actually. I should have, or did I fix it? I forget if I did. No, I didn't fix the typo yet. I have to fix a typo on homework 11, number 3. There's a typo. But let me give you a couple hints again, because as I said last week, this is traditionally, this stuff is, it's not easy to learn. So here's what you need to use for 1, 2, and 3. So we derived 2 of these in class, and then we stated the other ones. So you should check the lectures for that. Here's what we know. We know that 1 plus 2 plus 3 plus, keep this pattern all the way up to some number n. So we know that this is equal to, if we write it in sigma notation, we can shorthand it like this. And it has a very simple formula. It's n times n plus 1 divided by 2. So we actually derived this pattern in class. And then the next 2 we didn't derive, but we told you you could, and they're somewhat similar. Now, instead of adding each positive integer, I'm going to square them. And it turns out if you square them, there's a very nice pattern as well. How would you write that in sigma notation? It's this. And what's the pattern here? Well, it's n times n plus 1 times the quantity 2n plus 1 all over 6. So these are the formulas that you're using for 1 and 2.
Okay, wait. I don't get why you like how you got that n into n plus.
How I got the what part?
This second part, n into n plus 1, and then 2n plus.
Okay, so that's just okay. So there's 2 things you can do. You can either derive that. It's not obvious why it's true, but it is true. Verify for yourself. Do it for like n equals 3 and 4. You'll see that it's true. It's a formula. Now we derived the top one. We did that in class. You got to go back to what, last Tuesday or Thursday we derived that. The second one we didn't derive, but it is true. And if you want to see a derivation of it, if you want to see why it's true, just Google sum of squares formula. So you'll find lots of arguments why it's true. It might even be shown in the book. I'm not sure. Let me check. It might have the formulas. Now, it doesn't
So
derive them, but it is in the book.
this is
So,
the part where last time we did, like, we wrote 1 to 100 on top, then from down we started from 100 to 1, right? And then we
yes,
added them.
that was how we verified the top one. We did the specific case where n was 100, but that argument will work no matter what n is. You can replace, where I had 100, you can replace it with n, and you could do the same exact argument and derive that formula. Now, the formula for the second one is a little more complicated to derive, but you can absolutely do it. I'm just not going to spend class time doing it. You can trust me, or you can go derive it on your own. You can go to the internet and check it out. There's lots of different ways you can derive that formula. The key observation for you guys to make is that the left-hand side here, this is adding n things up. So if n is a really big number, that's a lot of calculation. Whereas no matter what, on the right-hand side, it's just a multiplication and a division. So we call these things on the right-hand side, we call these closed form of this sum. It's a very simple, right here, this right-hand side is a very simple expression for a sum that gets increasingly large as n gets large. And don't forget, what we really want to do is we want to study these sums when n is getting very, very large. In fact, we want to send n to infinity. And so it's nice to have these formulas. And then the last one that we stated is that you can also find a formula for the cubes. If I decide to cube everything instead of squaring it, well, we can write it in the shorthand like this. But what's the formula now? Now the formula is n squared times n plus 1 squared all over 4. So let me repeat what I said before. You can derive these if you'd like. We did the first one. The next two are a little more complicated, but if you search for them on the internet, you absolutely find them. Now, I am telling you, you don't need to memorize them, but you should do enough practice so that they become second nature. That's like anything. You don't, when you learn how to drive, you don't memorize the driver's manual. You go out and drive and you learn by doing.
Yeah, so what do you mean when you say derive it? Like, I still don't understand. Like,
okay, so I'm confused. So what do you mean you don't understand? If I tell you, I mean, look at this formula. Let's just example, take the one, how do I get, I'm circling this thing in red. When I say derive it, how do you get from the left hand to the right hand side? That's what I mean to derive. How do you get from this left hand sum to the right hand? That's what it means to derive. I'm telling you two things are equal, and it's not at all obvious why they're equal. So in order to convince somebody that they're equal, you have to do a derivation. You have to do some algebra. You have to do some sort of logical argument in symbols to show the left-hand side of the equation is equal to the right-hand side of the equation. So what I'm saying is, if you want to verify that the left and right-hand side of the equation are the same thing, you have to show a derivation. Does that make sense?
yeah, it does.
So yeah, it's not at all obvious. We did a derivation for the top one, the bottom two we did not. But again, you could easily find it on the internet. If you just type in it, if you just go to the Google machine and ask Google to do it, you'll find it.
Okay, so those derivatives are the same for any squared, yeah? Like any range of numbers that are squared and then any range of numbers that are cubed.
These formulas here, yes. Now look, maybe this is what's confusing you. When I keep saying a derivation, this has nothing to do with the derivative.
Okay.
What I'm writing on the board has nothing to do with the derivative.
I
So
just thought
you have to
that
be
maybe you're
you have
talking
to
of
be
that.
very careful here. I'm not, so maybe that's part of that might be sounding confusing. I didn't even think of that. This has nothing to do with derivatives. These are algebraic sums. You could have learned these sums in an algebra class. The only reason we're bringing them up right now is because they're useful when we do integration. But these things have nothing to do with taking a derivative like we were doing earlier this semester. So I'm using the English word derivative and derivation in two different contexts. So that might be part of the confusion.
Makes
All right. Does anybody else have a question about this? Okay. So if you look at the other problems, I'm asking you to work with the definition of the derivative. Now we've done the definition of the integral. We've done a few of these now. And it's something that you need to practice. Again, this stuff is challenging. It's conceptually difficult. And the fact of the matter is you're not going to learn it by watching me do it. And you're not going to learn it by watching or reading about it. You need to supplement that stuff with your own doing. You have to try these things and realize you're not going to get it right the first time. Even if you were quote unquote good at math before. Most human beings don't pick this up right away. It is a struggle to learn. So you have to keep that in mind when we're doing all this. So where does that leave us then? Well, it's going to leave us in this particular thing. So let me try to put a bow on this. So homework number 11 is giving you practice working with the definition. So it's working with Riemann sums and the definition of the integral. So let's not forget what this definition is, because it's actually quite complicated. So we have this new symbol, this elongated S, which is called an integration symbol. It has number at the bottom. It has a number at the top. These are called our upper and lower limits. And so what does this new symbol mean? Well, it means this. It means the following limit. And this is quite a scary looking creature. So I have now stated what these things mean over and over again, but I will say it one more time for full completeness. What do these symbols on the right-hand side mean? Delta x means b minus a divided by n. What is x sub k? Well, x sub k can be given by this formula. It's a plus k times delta x. That's a scary looking formula. And what do we know about x sub k? X sub k star can be any number between x sub k and x sub k minus 1. So this is an extremely complicated definition. We have worked with it for 3 days now. That doesn't mean we should know it. That doesn't mean it's easy.
So wait, is k always 1?
No, look where k can be. K can be 1, k can be 2, k can be 3, k can be 4. K goes between 1 and n.
Okay.
So how do I know that? How do I know that k starts at 1 and it goes 1, 2, 3, 4, 5 all the way up to n? Look at the sum here. The sum tells me k's first value is 1, then it's 2, then it's 3, then it's 4, and it goes all the way up to n.
To find x star k, we have to find first x k, right?
Yeah, but x sub q, but x star can be anything you want it to be as long as it's in between those two numbers.
So it doesn't have to be exact value. You can choose any value between those
It can
two.
be anyone, but you want to pick it in a useful way. So what I shared with you guys last week is you should let xk star be either xk or the previous one. Just put it to be either the left or the right one.
Okay.
Yeah. I always use the right Riemann sum, but you can use any one you want. Now, the whole purpose of problems like 3, 4, and 5 and 6 on this, 4, 5, and 6 on homework 11 is to give you practice working with this. It is not easy to do. And you'll notice that the problems I gave you, A and B, were 0 and 1. That's the best integral to practice on, or the interval to practice on, because it's easy to figure out what these x sub k's are. But you have to suffer through this if you want to learn it. Now, again, I've done it a few times for you, so I can't encourage enough. If you're still confused by it, you got to go back and watch that lecture over again. It's in there.
So
We've
there's
done it
0 and
twice
1,
now.
right?
What's
There's
that?
0 and 1.
Say that again.
There's 0 and 1. The interval 0 and 1.
Well, on problem 4, it's 0 to 1.
Yeah.
And
So
then on
do we
problem
replace
5,
it with n and k, or?
No. 0, 1, that's your A and B.
Okay.
And if you look at look how problem 4 is stated. I want you to do 4 first, a specific number of rectangles. Then I want you to do 8. Then I want you to do 40. And then I want you to, instead of doing a fixed number, I want you to let n be anything. It's the letter n. It's arbitrary. And then you send n to infinity in a limit. So again, you got to have to go watch that lecture and see. I did that problem. I did it for you. The problem's completely worked out. And a matter of fact, we've done this problem twice. We did it on Friday, and we even did it earlier in the week last week.
So one last question.
Yes.
So that n approaches infinity, right? Is it always there?
For the definition, yes.
Okay.
Notice in those problems I say approximate in A, B, and C.
Yeah.
If you don't take a limit, then it's just an approximation.
So every time you do it, you have to put that n approaches infinity, or?
Well, only when you're no, not for A, B, and C. For A, B, and C, n is a fixed number. So here's the problem you guys are going to have, and this is, it's not, you guys just do not have enough experience yet. So it's very difficult. It's for someone in this level of a math course. You guys, the idea of a fixed constant versus a variable still like confuse the hell out of you. Think about this. When you were in algebra class, you memorized the quadratic formula. You would write ax squared plus bx plus c. Right? You needed to understand that A, B, and C, even though you used the letter, they represented some fixed number. X was a variable. It was allowed to move around. It varies. Here, we are saying a similar thing. In the first 3 parts, in part A, B, and C of problem 4, I am telling you, you do not do a limit. You're doing a specific case, n equals 4. Then you're going to compute that. Then you're going to do the next specific case, n equals 8. Then you're going to do the next one, n equals 40. But while you're doing them, you're going to recognize there is a pattern. And the pattern you're going to see is this creature right here circled in red. You're going to see that. And so your goal is to then, once you recognize that pattern, you can take a limit of that as n goes to infinity. And that's what you're going to be doing. That's the definition of the integral.
So the limit thing is only there for part D.
Part D, that's correct.
Okay, so in others you don't use limit.
That's correct, yes.
And then what do you mean by over and underestimation?
Well, that's for you to think about. Draw a picture. And again, that's all explained. I explained it on Friday. And by the way, let me, if it's, I keep repeating myself, but that's okay. The first couple times you watch that, and it's not gonna make sense to you until you pause it and do it yourself, and then pause it and rewind. That's how you're gonna learn this. It's a very challenging thing to learn. Some of you will just say screw it, and you're not even gonna try to learn it. I think that's a bad philosophy to have, but some of you will do that. That's just the nature of how all these things work.
What's the name of that symbol S that looks like S?
That elongated thing with the numbers on it?
Yeah, what's the
That's
name
the
of
integral symbol.
Okay.
Okay, so all right, so what we need to do is we need to talk about some properties of the integral. So before stating properties of this creature, we need two definitions. So it turns out that this integral is very useful and important. And so if we want to use it for all it can be used for, we have to do the following. The first thing we want to do is ask ourselves, what if a and b are the same number? That is, what if f is some function and someone says, why don't we integrate from a to a of f? Well, essentially what I'm asking you to do, if you want to think of this from a geometric perspective, is this is asking, what is the area underneath a point? And if you want to even assign meaning to that, the only thing that makes any type of sense would be to assign the value 0 to this. If you integrate from 5 to 5, the integral is 0, no matter what f is. If you integrate from -6 to -6, the integral should be 0, no matter what f is. And then the next thing we have to ask ourselves is, what if the numbers, what if when we defined this thing, it was assumed that a was less than b? That's the only reason it made any sense. But what if we sort of have the idea to have it the opposite or flip them? Well, there's a very natural way to do this. If I want to integrate from b to a as opposed to a to b, that means I'm going the opposite direction. And if you worked out the math, the only logical thing to do would be to take the standard integral that we already defined and throw a minus sign in front. So these are two very, very important sort of mathematical objects that arise. These two things arise, so we have to assign meaning to them, and that's what I just did. Now, the next thing you should do is keep in mind what we're doing. We're we're defining a new mathematical object. It's called the integral. Now, what we have to keep in mind is this integral can have many, many, many interpretations. We are using one of them a lot. We're using the area interpretation. Why? Because it's intuitive. So we motivated this idea of an integral by asking questions about area. And so when we think about these facts about the integral, these theorems, these properties, you need to keep area in the back of your head. Because the reason that these things are true can intuitively be realized by drawing pictures. So what do I mean by that? Well, I mean the following. So these are properties of the integral. So the first one says that if I take two functions now and I want to add them together, we know I get a third function. Or if I take two functions and subtract them, I get a new function. And so I want to ask what happens when I try to integrate the sum or difference of two functions. Well, as we would hope, it turns out that you can just do each one separately. This is a very, very natural thing that we would hope. This essentially says that if we take two terms instead of one term, we can integrate each one separately. We will use this property a gazillion times the remainder of the semester. Well, actually not a gazillion. You might not live that long. But. Okay. The next important fact is that if I take any function and I multiply it by a constant, that constant is not varying. And so when we integrate, essentially the integral is not doing anything to that constant. So what does that mean in terms of integration? Well, if I have c times a function, where c is a constant, one of the very useful things is that I can pull this creature outside. You will use this over and over again. Another important fact that we will take advantage of is that I can take an integral and break it up in any way I'd like. So to illustrate what I mean, I have a sheet of paper right here. Sheet of paper, it's a rectangle. Every one of you would agree with me, even in your 5-year-old mind or your 5th grade mind or your university calculus level mind, that if I take this sheet of paper, no matter how I rip it, I now have two pieces. But you will all agree that if I take the area of this piece and I add it to the area of this piece, I will get the same area that if I started with my whole piece. The sum of the parts, the sum of the parts is the whole. So that makes sense in our brain. How do we write that in terms of integrals? Well, it means you can pick and break this up any way you like. So pick any number you want. We'll call it C. And so this says that I can break this up any way my heart desires. And what's very important to note about both the fact 2 and 3 is the following. These are true for any constant C.
So
Any constant. Yeah.
in part 3, right? does that C on top and that C down, are they the same thing or they're different?
Absolutely. That's why I use the same letter. It has to match.
Because one has a line going up, that's why.
I don't know why. That shouldn't look like that. Let me fix that. They're both C. So as long as the top one on the left and the bottom one on the right are the same number, then that is true. All right, let's list two more facts that are very important. Does anybody have a question before we move to the next page? And by the way, notice I called this a theorem. If you were so inclined, you can derive every one of these from that limit definition. We're not going to do that, but you could. Okay, the next very important fact is the following. I guess this is really the last one we need. If f of x is greater than or equal to g of x on our interval, then the integral of f of x, whatever number this is, it has to be greater than or equal to the integral of g of x. So this piece has two very important consequences that you should use, and they're very intuitive, and we'll take advantage of them later on. But make sure you understand this. So let's actually put this real important one right next. So in particular, if you have a function that's non-negative, then you know the value of your integral better be non-negative. Any questions? All right, so let's work with a couple of these. Let's see what kind of information we can deduce using what we already learned. So we already showed, and you're going to be asked to do this. So this was in class and homework. So what did we show? We know the integral from 0 to 1 of x squared is 1/3. And we're going to show, you're going to do in homework number 6, you're going to show the integral from 0 to 1. And I got typos galore in this homework. I never fixed them. I'm a terrible person. You're going to also show that this integral is 1/4. I guess we have 3 facts that we're going to show you. You're also, and I think we actually did this, did we not? Maybe, oh, we did it from 0 to 3. So let's do it that way. I believe we did that. And so this becomes 24 over 3. Excuse me. 27 over 3.
So how does that x squared and x cubed help?
How does what?
The x squared and x cubed, like in what way do they help?
I'm not quite sure what you're asking.
You're seeing the thing you have written, the integral you have written, right? There's an
Yeah.
x squared over there next to dx.
That's just notation.
Okay.
The
So
function I'm working with is x squared. And then in the next one, I'm giving you, we're working with x cubed. And then on the fact I'm giving you on the third fact, again, we did all of these in class. Well, the first and last one we did in class. The middle one you're doing for homework. These are facts. How do I know they're facts? Because we derived them. We took the limit, we did the Riemann sums, and we show that these are facts. And now we want to show how we can use these 3 facts to gain new information.
So do we actually use the function when we're finding the thing?
Oh, absolutely.
Okay.
I mean, you're gonna I mean, there's a pattern here that we're gonna learn about soon enough, but that x squared matters, that x cubed matters. Everything that I've written down matters. Okay, so some information we can deduce. Well, we have the following. So we can use those to compute unknown integrals. So let's do a couple of them. For example, if I wanted to integrate 0 to 1 of 3x squared plus 5x cubed dx, I can use those properties that I just stated. So this becomes the same as the integral from 0 to 1 of 3x squared dx. We can break it into 2. Integral 0, 1 of 5x cubed dx. Then I can pull out my constants. Then, of course, this is 3 times a third plus 5 times a fourth. Which is 27 over 12. So I was able to break down a new function and its integral in terms of known integrals using those integral properties. Does anybody have a question? Another exercise, or another, I was gonna say exercise, but another derivation we might make. If we go back, so I know something about the integral from 0 to 3 and 0 to 1 of x squared, so I can make the following observation. Suppose I wanted to integrate from, say, 1 to 3 of x squared dx. Well, I could, if I wanted to, I could break my sheet of paper into two, and I can do it in a creative way. So I don't know anything about 1 to 3, but I do know from 0 to 1, and I know from 0 to 3. So what I can do is I can introduce the bound of 0. I can say, okay, I'm going to put a 0 here. And then that means if I put a 0 down here, this is completely legal. So this was that property 3 we wrote. I broke it into 2 in a creative way. Okay, now I use property 2 to flip this. This is minus the integral from 0 to 1 of x squared. I'm using my integral properties. So, and I'll remind you of what they are in a second. So if you're interested in what I'm using, here I'm using property 3. And here I'm using, I think it was property 3. Let me go double check. Yes, it was property 3. And then here I'm using that definition 2. That says if you flip the bounds, you put a minus sign in front. Okay, now I know these integrals. This is negative a third, and then this is 27 over 3. And so if I do the arithmetic, I get 26 over 3. So think about that for a second. Let me know if you have a question. Or comment. Anybody going once?
No.
All right. So a couple things should be stated. This is not the most efficient way of calculating and some of you already know that there's a quote-unquote shortcut to all this. Anybody? All right. So, all right. So here's the important sort of questions, observations. So first off, bad news.
Wait, quick question.
So when we go to compute this guy, from the definition, it is usually very difficult.
Are we gonna have a final for this class or no?
We talked about that on Friday, Josh. Yes, there will be a final. No midterm. We're not gonna have a second midterm. We're gonna have a final.
Or
It'll be just like the other one. I'm going to explain all that stuff in detail probably in the next week or so. I'll put some stuff on Canvas to make it easy for you to understand. But yeah, we're going to try to make this as painless as possible going forward, because this is not ideal. All I hear is chaos above me. I have screaming kids. I don't know what's happening. They have no respect for our learning down here. Anyhow, yeah, so I'll go over all that probably in the next week or so. I'll post all that stuff to Canvas, and then we can move forward at that point. So what's the good news then? So the good news is there's often, not all the time, there's often an easier way. Now, of course, I'll put that in quotations because easier is a completely relative term. So this easy way is actually a powerful theorem. And it's called the fundamental theorem of calculus. So what's fascinating about this fundamental theorem is that it takes an extremely difficult calculation and oftentimes turns it into a simple piece of arithmetic. So does anybody have a question? Because it's important that we get this situated. We have to understand. So, you know, and this is very difficult, and I could tell it's difficult by all the questions you guys even have about the homework. One of the things that you need to appreciate and respect is that certain things we do in a math class specifically, we make definitions of things. And oftentimes, as you saw with the derivative even, the definition is a complicated mathematical operation. And then what we hope to do is we hope to develop some theoretical tools that make these complicated things easy. And so you'll go in your time machine and you'll think about the derivative. We defined it using this limit, and we had this thing like a difference quotient, and it was quite overwhelming for most of us. And then we turn around the next week and we learn this sort of quote unquote shortcut. But that shortcut was really, there's a lot of hard work that goes in behind the scenes that allows us to use those shortcuts. And there's going to be a very similar thing happening here. The fundamental theorem of calculus is this super powerful theorem that is going to take a very challenging and tedious computation, and it's oftentimes going to replace that with simple arithmetic. So it cannot be understated how important it is that you understand that what we're going to do is not obvious. And it's not obvious in the sense that the definition for this integral is quite complicated. And you're going to think, well, why did we study this ugly definition and these limits and these Riemann sums? Why didn't you just teach us this? And there's lots of ways I can answer that question, but the best way I'll answer it right now is you'll look over here. I didn't say, in the good news section, I didn't say there's always an easier way. I said there's often. So the operative word here is often. The fundamental theorem of calculus doesn't always work. But when it does work, it's extremely, extremely helpful. So that's where we're at now. So hopefully you appreciate this, and we're going to try to motivate it the best we can right now. Okay. Any questions, comments?
No.
All right, so here's how we're going to motivate it. We're going to do it the following way. What we're going to do is we study what are called area functions. So what is an area function? It's going to be the following. I'm going to define a function. I'm going to call it a of x, capital A of x. So instead of me writing f, I'm going to write capital A. And I'm going to define it like this. It's going to be the integral from lowercase a, which is some number, and then the upper limit is going to be the letter x. It's going to be a variable. And then I'm going to integrate f. Now, what I want you to understand is that I've already used the letter x, so I can't use the letter x again, so I need another letter to illustrate sort of my variable, so I'm going to switch this guy to t. So the couple things need to be pointed out about this. This is the input. My independent variable is x. What is A? A is the dependent variable because it depends on x. What is t? Well, this is often confusing for us. T is the variable of integration. I can't use x in two different contexts here. If I would put x upstairs and then also put f of x dx, that would be completely misleading. So I need to introduce a new letter. Now, this is not new to you. You guys understand that. So, for example, let me remind you of all I'm suggesting. When you were in an algebra class, you guys all know that f of x equals 3x squared and f of t equals 3t squared. Whoa. These guys are this, really, bro? I hate this pen. So these are the same function. So it doesn't matter what letters I use, as long as I'm consistent. Does anybody have a question? All right, so we're going to study this function. Some nice things pop up when we study it. So before we do that, let's think about why we call it an area function. Well, let's think about what it's doing. It's the integral. So we can interpret it as an area. So if I just draw some arbitrary function, so suppose this is my function y equals f of t. So that means my horizontal axis would be the t-axis. This vertical axis is my y-axis. Let's say this is the starting point A, and let's say this is x. So I'm going to shade in this region between the curve and the x-axis. And the observation to make here is that a of x is this integral, the integral from a to x of f of t dt. But what is this? Let's not write it in math terms. Let's write it in elementary children terms. It's the area. In this case, we have to be very specific, net of the red region. So this is why we call it an area function, because it's giving us the net area of something. Now, if you're confused by this term net area, you need to go back to last week and look at the lecture when we talked about that. Does anybody have a question about this? All right, look, let's look at a very specific one. We'll start with the simplest cases, and let's think about what's happening. So here's what I want to do. I want to consider the following functions. Let's take f of t. Let it equal a line. So let's just say f of t equals t. This is like the line y equals x. So what is this? If you want to think about its graph, this is line with slope. Actually, let's start even simpler. Let's just start with a constant. That'll be even easier for us to see. We'll do two very basic cases. So let's start with f of t equals, let's say 3. So this is the horizontal line y equals 3. So let's study it on 0, comma x. So let's draw this picture. Here's my t-axis. Here's my y-axis. So let's put this 1, 2, 3. So let's draw the graph. And so let's just pick some number, some space, we'll call this x. And then let's shade in the area under the curve there like we did before. Now, why did I start us with this particular example? Well, because this is a very familiar shape to everybody. I could bring in a bunch of fifth graders and ask them what the area is. So let's compute a few values just using some basic mathematics, arithmetic, say. So let's note some very simple things. What is A of, say, 1? Well, A of 1 is nothing more than this rectangle. So how can we write A of 1? Well, we can write it in grown-up terms. We can say this is the integral from 0 to 1 of 3 dt. But what is that really? What is it? It's a rectangle of width 1, height 3. So you could think of that as 1 times 3. What's A sub 2? That's the integral from 0 to 2 of 3 dt. And of course, if you do that, its width is 2, its height is 3. You can play this game all the way down to whatever x is. What's x? Well, that would be the integral from 0 to x of 3 dt. And using the length times width, this is just x times 3. Does anybody have a question about this? So the observation to note is you're seeing a pattern here. Now there's lots of patterns, so maybe you're not thinking of the pattern that I'm seeing. But if I come down here and I make, if I come down here, what is the observation that I'm making? I'm making the following observation. The integral from 0 to x of 3 dt is just equal, if I write this, I'll just write it as 3x. Or another way of saying that is that a of x is equal to 3 of x. So what I was able to do is I was able to not have to write this integral. I can come up with a very simple formula for the area under the curve. Why? Because this particular function is a horizontal line. Its graph is a horizontal line. And so the area underneath it is nothing more than the length times width of a rectangle. Does anybody have a question about this? All right, so let's instead of doing a horizontal line, let's take a line that does not have slope 0. So this time the function f of t I'm going to use is I'm going to use f of t equals t. On 0x, and I'm going to play the same game I just played. So if I take my function and I graph it, this is what the graph looks like. So this is the line of slope 1. It goes through the y-axis at 0. So this is like the point 1, 1, 2, 2, etc. Up here, this would be the point x, x. So this input is x. And so now this graph, if we think about what we have, is we have the following. We have a triangle. So what is, for example, a of 1? Well, the integral from 0 to 1 of t dt, that's a triangle of base. So this is 1/2 the base times the height. And then what is a sub 2? Well, that's the integral up to 2 of t dt. And if we recognize it as a triangle, it's 1/2 the base times the height. And so in general, what we recognize is that the area function this becomes 1/2 times x times x. So if we just sort of write off again what that is in general, the area under the curve of this function in particular is 1/2 x squared. All right, let's do one more to see if we recognize a pattern. What is happening? All right, we have crying upstairs. Chaos. All right, so I want to do one more of these, but I want you to recognize the pattern that in this first example, there's a connection between what's inside the integral and the actual area. In this example, there's a connection between what's inside the integral and the area. And we're gonna write this down again, but it's worthwhile doing one more example. And then maybe we'll see a pattern. So now I want f of t to be t squared, the parabola on 0x. So once again, I make my axis. Now I have to draw my parabola. So that's a curve that looks like this. So we know if this is the point x, that this point right here is x comma x squared. And now this is not an elementary geometric shape, but we do know what this area is. we've done it before. We asked you to do it for homework. We made an observation. So here, a of 1 is the integral from 0 to 1 of t squared dt. And we know what this is. This is 1/3. We did it already. A sub 2 is the integral from 0 to 2. You're doing this from homework. So you're going to recognize that this is 8/3. And then we did this one on Friday, a sub 3. That's the integral from 0 to 3 of t squared dt. And we found that to be 27/3, which is 9. So in general, what is the area up to x? Well, we alluded to this for you guys last week. I encouraged you to convince yourself it's true by doing it. You could show that this is x cubed over 3. So the first two examples were not difficult because it was a rectangle and then it was a triangle. Those formulas for their area are well known. This one, the stuff that I'm writing here is not obvious from the picture. It's obvious from what we did in previous classes. So here's the key observation. And I'm going to write it on the next slide. And you're going to have to take some time to think about this. In the first example, what we showed is we showed the integral from 0 to x of 3 dt was equal to 3x. In the second guy, we showed the integral from 0 to x of t dt was equal to what? It was 1/2 x squared. And then in the last example, what we showed is if you do t squared up to some variable bound, you get 1/3 x cubed. And so if you spend some time pondering this, you see a pattern. You might see more than one pattern. Well, if you take the right-hand column, if you take the derivative of 3x, what do you get? You get 3. If you take the derivative of 1/2 x squared, you get x. If you take the derivative of 1/3 x cubed, you get x squared. So what it's really saying, or at least suggesting, is the following. So these three examples suggest the following general fact. They suggest that if a of x looks like this, then the derivative of a is just the function. So this seems like a lot of very insane, scary symbols, but let's put it in a language you might understand. In words, integration and differentiation are inverse operations. Just like adding and subtracting undo each other. Multiplication and division undo each other. Square roots and exponent power 2 undo each other. The derivative and the integral are inverses. They undo each other. That's what we're thinking. Why are we thinking that? Look at the previous 3 examples. There's a pattern there. It might not be obvious to you right now, but if you spend some time and think about it, you will see a pattern. Again, look at the right-hand side. Take the derivative, you get what's inside. Take the derivative, you get what's inside. Take the derivative, you get what's inside. Now, of course, you're going to say, well, that's a t. But again, t squared and x squared are the same mathematical object. Just like y squared is the same thing. The letters are immaterial. So you really need to think about that. Because this fact right here, this fact that a prime of x is just what's inside, that fact is going to be the hidden piece to making integration very simple. The last thing I'll say is if we rewrite this, it looks even more like inverse operations. If I take the derivative of an integral, whoops, I'm lying to you. If I differentiate an integral, I just get what I started with. Remember, we work from the inside out. The first thing I'm doing to f is I'm integrating it. And then after I integrate it, then I'm differentiating it. And this formula tells me that I get what I start with. It's crazy. All right, that's a good place to stop. Does anybody have a question? We did a lot today. It's overwhelming. Any questions at all? All right, then. I will hopefully see you guys on Thursday.